When we first learn about atoms, the idea seems simple enough. Tiny building blocks stacked together to make everything around us. Over time, however, this simple picture begins to dissolve into something far more strange and fascinating. The deeper physics looks into matter, the clearer it becomes that atoms are not solid little balls packed tightly together. Instead, they are vast regions of emptiness, structured by forces, motion, and probability. And yet, despite this overwhelming emptiness, matter feels solid, reliable, and resistant. This apparent contradiction sits at the heart of how nature truly works. An atom consists of a nucleus at its center and electrons that exist around it. The nucleus itself is incredibly small compared to the overall size of the atom, yet it contains almost all of the atom's mass. Protons and neutrons are tightly bound within this nucleus, while electrons occupy regions far away from it. If we imagine scaling an atom up to a size that is easy to picture, the nucleus would be like a grain of sand placed at the center of a large sports stadium, while the electrons would be like a few tiny insects buzzing near the outer seating. Everything in between would be empty space. This emptiness is not just a small gap. It is the defining feature of atomic structure. More than 9,900,999,999,999% of an atom is empty space. That means every object you can see, touch, or hold is mostly nothing. Your body, the ground beneath your feet, the air around you, even the densest metals, are all composed of atoms that are overwhelmingly empty. At first glance, this seems impossible to reconcile with everyday experience. If things are mostly empty, why don't we fall through the floor? Why does a wall stop us? Why does a table feel hard? The answer lies not in the presence of solid material filling space, but in the forces that operate within that space. What gives matter its solidity is not matter itself, but interaction. When atoms come close to one another, their electrons interact through electromagnetic forces. These forces are incredibly strong and act over extremely small distances. When you press your hand against a table, the electrons in your hand are repelled by the electrons in the table. This repulsion happens so quickly and so powerfully that it feels like contact, even though no atoms ever truly touch in the classical sense. This idea challenges our everyday intuition because we tend to associate solidity with substance. We imagine that hard objects are hard because they are filled with something dense and unyielding. In reality, hardness is a consequence of organized electric forces resisting change. The table does not resist your hand because it is full, but because its atomic structure is stable, and its electrons are arranged in such a way that they strongly oppose being pushed closer together. Another layer of this explanation comes from quantum mechanics, which tells us that electrons are not tiny particles moving along neat circular paths. Instead, they exist as probability clouds spread out over regions of space. These clouds define where electrons are likely to be found, not where they are at any exact moment. When two atoms approach each other, their electron clouds begin to overlap, and quantum rules prevent electrons from occupying the same state. This restriction, known as the Pauli exclusion principle, plays a crucial role in creating the resistance we experience as solidity. The Pauli exclusion principle states that no two electrons can share the same quantum state. When atoms are pushed too close together, electrons are forced into higher energy states, which requires energy. Nature resists this increase in energy, and that resistance manifests as a force pushing the atoms apart. This is one of the deepest reasons why matter does not collapse into itself, and why solid objects maintain their shape. From this perspective, solidity is an emergent phenomenon. It is not a fundamental property of matter, but a collective effect arising from countless interactions at the atomic and subatomic level. Billions of atoms, each obeying the same simple rules, give rise to the stable, solid world we inhabit. The chair you sit on feels solid not because it is filled with material, but because its atomic structure forms a persistent pattern of forces that resists disruption. Richard Feynman often emphasized how misleading common language can be when talking about physics. Words like empty and solid carry meanings shaped by human experience, not by atomic reality. When physicists say atoms are mostly empty space, they do not mean empty in the sense of useless or inactive. That space is alive with fields, energy, and motion. Electric fields extend outward from charged particles, magnetic fields arise from moving charges, and quantum fields permeate all of space. These fields are what mediate interactions, transmit forces, and ultimately give matter its physical properties. Even the concept of touch becomes questionable at the atomic level. What we perceive as touch is actually the sensation produced when electromagnetic forces prevent our atoms from moving into the same space as the atoms of another object. There is no direct contact in the classical sense, only force interactions that our nervous system interprets as pressure or hardness. This realization transforms something as ordinary as touching a surface into a subtle dance of invisible forces. The emptiness inside atoms also explains why matter can be compressed under extreme conditions. In everyday life, the electromagnetic and quantum forces between atoms keep them at fixed distances, giving materials their shape and volume. But under enormous pressure, such as inside stars or during violent cosmic events, atoms can be forced much closer together. In white dwarf stars, electrons are squeezed into a dense state where quantum effects dominate. In neutron stars, atoms collapse entirely, and matter becomes so dense that protons and electrons merge into neutrons. These extreme cases reveal that what we think of as solid matter is only stable under certain conditions. The fact that atoms are mostly empty also allows for the existence of waves, radiation, and particles passing through matter. Neutrinos, for example, pass through Earth in vast numbers every second without interacting with atoms at all. They slip through the empty spaces and weakly interacting fields that make up matter. Even high-energy radiation can penetrate materials, revealing once again that solidity is not an absolute barrier, but a statistical outcome of interactions. At a deeper philosophical level, the emptiness of atoms forces us to reconsider what we mean by real. If most of matter is empty space, then reality is not about solid stuff occupying volume, but about relationships and interactions. The structure of the universe is less like a pile of bricks and more like a web of forces and probabilities. Objects are defined not by what they contain, but by how their components behave together. This understanding also highlights the extraordinary effectiveness of physical laws. Simple rules governing charge, motion, and quantum states are enough to produce the rich diversity of materials we observe. Metals conduct electricity because of how their electrons move freely within atomic lattices. Insulators resist current because their electrons are tightly bound. Diamonds are hard because of strong, rigid bonding between carbon atoms, while graphite is soft because of weaker bonding in certain directions. All of these differences arise from variations in how empty space and forces are organized at the atomic level. From a human perspective, It is remarkable that such an abstract and invisible structure gives rise to such a tangible world. We navigate our lives based on the assumption that objects are solid and reliable, and for all practical purposes, they are. Physics does not deny this experience, it explains it. Solidity is real, but it is real in a deeper, more subtle way than our senses suggest. Feynman loved to remind people that understanding physics does not remove the beauty of the world, it enhances it. Knowing that a flower is made of atoms does not make it less beautiful, and knowing that those atoms are mostly empty does not make the flower less real. Instead, it adds layers of wonder. The fact that emptiness, guided by simple laws, can produce color, texture, strength, and life is one of the most astonishing achievements of nature. In the end, the idea that atoms are mostly empty space, yet matter feels solid, teaches us humility. It shows us that our senses evolved to navigate survival, not to reveal ultimate truth. Beneath the surface of everyday experience lies a world governed by principles that are subtle, counterintuitive, and profoundly elegant. Solidity is not a fundamental ingredient of the universe, but a remarkable illusion born from order, interaction, and the ceaseless activity of forces in what we once thought was empty space. From the moment we interact with the physical world, we instinctively assume that structure comes from substance. We believe things hold their shape because they are made of something firm and resistant, as if matter itself were the source of stability. A bridge stands because it is built from steel, a mountain exists because it is made of rock, and our bodies remain intact because they are composed of flesh and bone. Yet when physics looks beneath these appearances, it reveals a deeper truth. Structure does not arise from material substance alone, but from forces. It is the invisible interactions between particles that determine how matter organizes itself, how it holds together, and how it behaves. At the atomic level, substance loses the solid meaning we attach to it in daily life. Atoms are not compact objects packed tightly together like grains of sand. They are systems of particles held in place by forces. Protons and neutrons cluster in the nucleus due to the strong nuclear force, one of the most powerful interactions in nature. Electrons are bound to the nucleus by electromagnetic attraction, forming stable atomic structures. Without these forces, there would be no atoms at all, only a chaotic sea of particles drifting aimlessly through space. What we recognize as structure, from the simplest atom to the largest galaxy, is the result of balance. Forces pull things together, push them apart, and shape their arrangements. In atoms, electromagnetic attraction draws electrons toward the nucleus, while quantum rules and electron repulsion prevent them from collapsing inward. This balance creates stable electron configurations, which in turn define the chemical identity of each element. Hydrogen behaves differently from carbon, not because its substance is inherently different in a mystical sense, but because the forces within its atom are arranged differently. As atoms combine to form molecules, forces again take center stage. Chemical bonds are not physical glue. They are manifestations of electromagnetic interactions. When two atoms bond, their electrons rearrange themselves into configurations that lower the total energy of the system. Covalent bonds share electrons, ionic bonds transfer them, and metallic bonds allow them to move freely through a lattice. In every case, structure emerges from how forces guide electrons into stable patterns. The molecule holds together not because it is filled with solid matter, but because breaking it apart would require overcoming the forces that bind it. These molecular structures scale upward into the materials we encounter every day. The hardness of diamond, the flexibility of rubber, and the brittleness of glass all arise from the way atoms are bonded and arranged. Diamond is hard because each carbon atom is locked into a rigid, three-dimensional network of strong covalent bonds. Rubber is elastic because its long molecular chains can stretch and return to their original shape due to weaker intermolecular forces. Glass shatters because its atomic structure lacks the ability to rearrange under stress. In all cases, structure is a story written in forces, not in the presence of dense substance. Even at larger scales, forces remain the architects of structure. Gravity shapes planets, stars, and galaxies. It pulls matter together over vast distances, forming cosmic structures that span billions of light years. A star exists because gravitational collapse is balanced by the outward pressure generated by nuclear fusion in its core. Planets maintain their orbits because gravitational attraction is balanced by their motion through space. Without gravity, matter would not clump together into meaningful forms. It would remain dispersed and formless. What is striking is that forces operate without regard for our intuitive sense of solidity. Gravity acts on mass regardless of whether that mass is solid, liquid, or gas. Electromagnetic forces act on charge, not on material hardness. The strong nuclear force binds quarks together inside protons and neutrons, and binds those particles inside atomic nuclei, even though the distances involved are unimaginably small. Structure persists not because matter is solid, but because forces enforce order. This understanding challenges the idea that space filled with substance is what gives objects their form. In reality, much of what we call structure exists in regions that contain very little matter at all. A crystal lattice, for example, is mostly empty space between atoms, yet it maintains a precise geometric form. The lattice persists because the forces between atoms define equilibrium positions, move an atom slightly out of place, and restoring forces pull it back. Push too hard, and those forces can no longer maintain the structure, causing the material to break or deform. The same principle applies to biological structures. Cells, tissues, and organs are not held together by solid filling, but by molecular forces. Proteins fold into specific shapes because of interactions between their constituent amino acids. DNA maintains its double helix because of hydrogen bonds and stacking interactions between base pairs. Muscle contraction occurs because molecular motors generate forces that slide protein filaments past one another. Life itself is an intricate choreography of forces operating at the molecular scale. One of the most profound implications of this force-based view of structure is that material identity becomes secondary. The same particles can form radically different structures depending on how forces arrange them. Carbon atoms can form diamond, graphite, graphene, or complex organic molecules. The substance is the same, but the structure changes because the bonding forces and arrangements differ. This reveals that matter is less about what it is made of and more about how it is organized. Richard Feynman often highlighted this idea to break the illusion that matter is fundamentally solid. He emphasized that what we feel as resistance or hardness is the result of electromagnetic forces between electrons. When you sit on a chair, you are not supported by solid substance in direct contact with your body. Instead, your atoms are held above the chair's atoms by repulsive forces that prevent them from occupying the same quantum states. The chair supports you not by touching you, but by pushing back through invisible interactions. This perspective also explains why materials can behave so differently under different conditions. Heat, for example, is a measure of how much particles vibrate due to energy. As temperature rises, atomic vibrations increase, stretching and weakening the forces that hold structures together. Eventually, a solid melts into a liquid, as these forces can no longer maintain fixed positions. Add more energy, and the liquid becomes a gas, where particles move freely and forces only weakly constrain them. At every stage, the substance remains the same, but the balance of forces changes, leading to different states of matter. In extreme environments, forces can create structures that defy everyday experience. Inside neutron stars, gravity overwhelms electromagnetic forces, crushing atoms until electrons and protons merge. The resulting matter is unimaginably dense, supported not by conventional solidity, but by quantum forces arising from the Pauli exclusion principle. Even here, structure is maintained by forces, not by solid filling of space. The realization that forces define structure also reshapes how we think about emptiness. Empty space is not irrelevant or passive. It is the arena in which forces operate. Fields extend through space, transmitting interactions from one particle to another. An electron can influence another electron across a distance because the electromagnetic field fills the space between them. Remove the field, and the force disappears. Structure collapses not when substance vanishes, but when forces are disrupted. This idea has deep philosophical implications. It suggests that reality is relational rather than materialistic in the traditional sense. Objects do not exist as isolated chunks of substance. They exist as systems of relationships governed by physical laws. A table is not simply there because it is made of wood, but because countless forces are working together to maintain its form. Change those forces, and the table ceases to be what it is. Understanding structure as force, driven, does not make the world feel less real. On the contrary, it reveals a deeper level of order and reliability. Forces follow precise mathematical laws. They behave consistently across space and time. This consistency is what allows structures to endure, from atoms that last billions of years to galaxies that persist across cosmic history. The stability we rely on in daily life is a direct consequence of the reliability of these interactions. In the end, recognizing that forces, not material substance, define structure transforms our view of the universe. It teaches us that what appears solid and permanent is, at its core, dynamic and interactive. Matter holds together not because space is filled with stuff, but because invisible forces continuously act to maintain balance and order. The universe is less a collection of solid things and more a vast, interconnected web of interactions, where structure emerges wherever forces find equilibrium. When we imagine empty space, we usually think of absolute nothingness, a silent void where nothing exists and nothing happens. This idea feels natural because our everyday experience associates emptiness with absence. An empty room contains air, but remove the air and we imagine a perfect vacuum, a place where there is truly nothing at all. Modern physics, however, paints a very different picture. What we call empty space is not empty in the classical sense. It is filled with quantum fields, and these fields are as fundamental to reality as matter itself. According to quantum theory, particles are not independent objects floating in space like tiny grains of dust. Instead, they are excitations of underlying fields that exist everywhere. An electron is not just a point particle, it is a ripple in an electron field. A photon is a vibration in the electromagnetic field. These fields extend throughout all of space, even in regions where no particles are present. This means that space itself has physical properties. It can store energy, transmit forces, and influence how particles behave. The idea of fields replaces the older notion that forces act mysteriously at a distance. In classical physics, electric and magnetic forces seem to leap across empty space, pulling or pushing objects without any visible connection. Fields provide the missing link. A charged particle alters the electromagnetic field around it, and another charged particle responds to that altered field. The interaction does not require direct contact or solid material in between. The field fills the space and carries the influence. Quantum fields take this idea further by showing that fields are not static or passive. They are dynamic entities governed by quantum rules. Even in the lowest possible energy state, known as the vacuum state, quantum fields are not completely still. They undergo constant fluctuations. Energy briefly appears and disappears, creating temporary disturbances in the fields. These fluctuations are not just theoretical curiosities. They have measurable effects, such as the Casimir effect, where two uncharged metal plates attract each other in a vacuum due to changes in quantum field energy. This restless nature of the vacuum challenges the idea that emptiness is nothing. Empty space is more accurately described as a seething background of potential. Particles can emerge from it, interact, and vanish back into it. In high-energy environments, such as near black holes or during the early moments of the universe, the energy stored in quantum fields can give rise to real particles. Matter itself can be seen as a temporary expression of deeper, underlying fields. One of the most profound implications of quantum fields is that they blur the distinction between particles and space. Space is no longer just a stage on which particles move. It is an active participant in physical processes. The properties of particles, such as mass and charge, are determined by how they interact with fields. The Higgs field, for example, gives certain particles their mass through interaction rather than by containing mass as a substance. Without this field filling space, many particles would behave as if they were massless. Quantum fields also explain why forces have the range and strength they do. The electromagnetic field has an infinite range, allowing light to travel across the universe. The strong nuclear force, by contrast, is confined to extremely small distances because of the nature of the field that carries it. These differences arise not from the particles themselves, but from the structure and behavior of the underlying fields. Space, filled with different fields, becomes a complex environment where interactions are shaped by field dynamics. From this perspective, what we call empty space between atoms is actually a dense web of overlapping fields. The electron fields of different atoms overlap, leading to interactions that create chemical bonds and material properties. Even in the regions between atoms where there are no particles, fields still exist and influence behavior. This is why forces can act across these regions, and why matter can maintain structure without being filled with solid substance. The existence of quantum fields also reshapes our understanding of energy. Energy is not only something that particles carry, it is also something that fields possess. The vacuum energy associated with quantum fields contributes to the overall energy content of the universe. On cosmological scales, this vacuum energy may be related to dark energy, the mysterious phenomenon driving the accelerated expansion of the universe. Once again, what appears empty turns out to be a dominant factor in shaping reality. Richard Feynman often emphasized that physics does not strip the world of mystery. It replaces old mysteries with deeper ones. The idea that space is filled with invisible fields may seem abstract, but it provides a coherent explanation for a wide range of phenomena, from the stability of atoms to the behavior of light. It reveals that the universe is not built from solid blocks placed in empty space, but from patterns of activity in fields that exist everywhere. This view also changes how we think about existence itself. If particles are excitations of fields, then their individuality becomes less absolute. An electron here is fundamentally the same as an electron anywhere else because it is an expression of the same underlying field. What distinguishes one situation from another is not the substance involved, but the configuration of fields and their interactions. Reality becomes a story of patterns rather than objects. The presence of quantum fields in empty space also means that nothing can be completely isolated. Every particle interacts, however weakly, with the fields around it. Even in deep space, far from stars and galaxies, quantum fields are present. This interconnectedness suggests that the universe is fundamentally unified. There is no true separation between matter and space, only different modes of excitation within the same underlying framework. At a human level, this understanding is both humbling and inspiring. It shows that the solid world we experience emerges from something far less tangible than solid substance. Our senses evolved to navigate a world of surfaces and resistance, not to perceive fields and fluctuations. Yet beneath those surfaces lies a reality that is more subtle and more dynamic than our intuition suggests. Empty space, once thought to be nothing, turns out to be everything's foundation. It supports the existence of particles, enables forces to act, and shapes the evolution of the cosmos. When we say that space between atoms is filled with quantum fields, we are not using poetic language. We are describing a measurable, testable aspect of nature that underlies all physical phenomena. In the end, the idea that quantum fields fill empty space invites us to rethink the meaning of emptiness itself. Emptiness is not absence but potential. It is not silence but a quiet hum of activity governed by precise laws. The universe is not constructed by placing matter into a void. It emerges from the continuous, ever-present fabric of fields that fill all of space and give rise to everything we observe. When people hear the word vacuum, they usually imagine perfect emptiness, a condition where absolutely nothing exists. In everyday language, a vacuum cleaner creates a vacuum by removing air, and we naturally extend this idea to mean that if all matter is removed, nothing remains. Classical physics once supported a similar picture, treating empty space as a passive void where objects could move, but where nothing of physical significance happened. Modern physics has completely overturned this view. What we call a vacuum is not empty at all. Even in the absence of particles, energy fluctuations are constantly taking place, revealing that emptiness itself is alive with activity. At the heart of this idea lies quantum mechanics, a theory that reshaped our understanding of nature at the smallest scales. Quantum mechanics tells us that energy cannot behave in the smooth, continuous way we expect from everyday experience. Instead, it is governed by uncertainty. Certain pairs of physical quantities, such as energy and time, cannot both be precisely defined at the same moment. This principle means that for extremely short periods, energy can fluctuate, appearing and disappearing without violating the fundamental laws of physics. These fluctuations are not mere mathematical tricks. They are real physical effects that can be measured and observed. In a quantum vacuum, fields cannot be perfectly still. Even in their lowest possible energy state, they possess what is known as zero-point energy. This is the minimum energy that a quantum system can have, and it cannot be removed. As a result, fields are always gently vibrating, even when no particles are present. One way to visualize this is to imagine a perfectly calm ocean. Classical thinking would suggest that if the wind stops and all disturbances vanish, the water should become completely flat. Quantum physics tells us that this never truly happens. There is always a subtle, restless motion beneath the surface. Similarly, the vacuum is not a flat, featureless nothingness, but a sea of microscopic fluctuations, constantly rising and falling. These fluctuations give rise to temporary particles known as virtual particles. They are not particles in the usual sense because they cannot be directly observed traveling freely through space. Instead, they exist briefly during interactions, borrowing energy from the vacuum and then returning it almost immediately. Their existence is fleeting, but their effects are real. They contribute to forces, influence particle behavior, and even alter the properties of space itself. One of the most striking demonstrations of vacuum energy fluctuations is the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they experience a tiny attractive force. This force does not come from gravity or electromagnetism in the conventional sense. It arises because the presence of the plates alters the quantum fluctuations of the vacuum between them. Certain energy modes are suppressed between the plates, creating a difference in vacuum energy compared to the surrounding space. This imbalance produces a measurable force, confirming that vacuum energy is not an abstract concept, but a physical reality. Vacuum fluctuations also play a crucial role in the behavior of atoms. The energy levels of electrons are not determined solely by the electromagnetic attraction between electrons and the nucleus. They are slightly shifted by interactions with vacuum fluctuations. This phenomenon, known as the Lamb shift, was one of the early experimental confirmations of quantum electrodynamics. It showed that even empty space affects atomic structure, subtly modifying the energy of electrons. The influence of vacuum energy becomes even more dramatic in extreme environments. Near black holes, for example, the intense curvature of spacetime affects quantum fluctuations. This leads to a process known as Hawking radiation, where particle-antiparticle pairs formed near the event horizon can be separated, with one falling into the black hole and the other escaping into space. Over vast timescales, this process causes black holes to lose mass and eventually evaporate. Here, vacuum fluctuations are not just a background detail. They drive the evolution of some of the most extreme objects in the universe. In the early universe, vacuum energy fluctuations may have played a fundamental role in shaping cosmic structure. According to modern cosmology, tiny quantum fluctuations present during the universe's earliest moments were stretched by rapid expansion, becoming the seeds of galaxies and large-scale structures. The distribution of matter we observe today may trace its origins back to these minute variations in vacuum energy, amplified across cosmic distances. This idea profoundly alters our understanding of creation and existence. It suggests that structure can arise from what appears to be nothing. The vacuum is not a barren emptiness waiting to be filled with matter. It is an active participant in the universe's evolution. Matter and energy emerge from it, interact with it, and are influenced by it at every level. The existence of vacuum energy also raises deep questions about the nature of reality. If empty space contains energy, then space itself is a physical entity, not just a backdrop. It has properties, dynamics, and measurable effects. This challenges the classical separation between something and nothing. The line between existence and non-existence becomes blurred, replaced by a continuum of activity governed by quantum laws. One of the most puzzling aspects of vacuum energy is its connection to cosmology. Observations suggest that the expansion of the universe is accelerating, driven by a mysterious form of energy often called dark energy. One possible explanation is that dark energy is related to the energy of the vacuum itself. If so, then the tiny fluctuations occurring everywhere in empty space collectively dominate the large-scale behavior of the cosmos. The emptiest regions of space could hold the key to understanding the universe's ultimate fate. Yet this idea also presents a profound mystery. Theoretical calculations of vacuum energy based on quantum field theory predict values that are enormously larger than what is observed cosmologically. This discrepancy, sometimes called the vacuum catastrophe, is one of the greatest unsolved problems in physics. It suggests that our understanding of vacuum energy is incomplete, and that deeper principles remain to be discovered. Richard Feynman often spoke about the importance of embracing such mysteries rather than fearing them. For him, the strange behavior of the vacuum was not a failure of science, but a sign that nature is richer and more subtle than our intuitions allow. The idea that nothingness can fluctuate, exert forces, and shape the universe invites a sense of wonder rather than discomfort. From a philosophical perspective, vacuum fluctuations challenge long-standing ideas about being and nothingness. For centuries, thinkers debated whether nothing could exist at all. Quantum physics offers a surprising answer. What we call nothing is actually something governed by laws, full of activity, and capable of producing real effects. Emptiness is no longer the absence of reality, but a fundamental aspect of it. At the human scale, these ideas may seem distant and abstract, far removed from daily life. Yet they underpin the stability of atoms, the behavior of materials, and the evolution of the cosmos. The fact that your body, the ground beneath your feet, and the light reaching your eyes are all influenced by vacuum fluctuations connects the most ordinary experiences to the deepest workings of nature. In the end, the existence of energy fluctuations in a vacuum teaches us a powerful lesson. Reality is not built solely from tangible objects and visible matter. It emerges from deeper layers of activity that operate even in apparent emptiness. The vacuum is not a void, but a foundation, humming quietly with energy, shaping the universe in ways both subtle and profound. What we once called empty space turns out to be one of the most important and mysterious ingredients of all that exists. When we look at the world around us, it feels natural to think in terms of objects. A chair is an object, a tree is an object, a person is an object, each one separate, self-contained, and defined by its physical boundaries. This way of thinking is deeply rooted in everyday experience and language. Yet modern physics suggests that this object-centered view is not the deepest way to understand reality. At the most fundamental level, what matters is not isolated things, but interactions. Reality is shaped more by relationships and processes than by solid, independent entities. At the atomic scale, this shift in perspective becomes unavoidable. An atom is often described as a thing, but in practice, it is a system of interactions. The nucleus exists because protons and neutrons are bound together by the strong nuclear force. Electrons remain associated with the nucleus because of electromagnetic attraction, balanced by quantum principles that prevent collapse. Remove these interactions, and the atom ceases to exist as an atom. There is no independent object left behind. The identity of the atom is inseparable from the forces acting within it. This relational nature extends to how atoms interact with one another. When atoms form molecules, they do not merge into a single solid lump. Instead, they enter into stable patterns of interaction. Chemical bonds are not physical connections in the ordinary sense. They are relationships defined by shared or transferred electrons and the energy configurations that result. A molecule is less like a glued-together object and more like a coordinated dance, where each atom's behavior depends on the others. At larger scales, materials themselves can be understood as networks of interactions. The rigidity of a crystal, the flexibility of a polymer, and the flow of a liquid all arise from how particles interact over time. Even the distinction between solid, liquid, and gas is not about the substance changing its identity, but about changes in interaction strength and organization. In a solid, interactions strongly constrain motion. In a liquid, interactions allow movement while maintaining cohesion. In a gas, interactions are weak and fleeting. The object changes its behavior because the relationships between its components change. This interaction-based view also clarifies why objects resist one another. When you push against a wall, it feels like you are encountering a solid barrier. In reality, what you experience is a complex set of electromagnetic and quantum interactions between the atoms in your hand and the atoms in the wall. Your hand does not collide with a solid surface in the classical sense. Instead, overlapping electron clouds and quantum rules generate forces that prevent further penetration. The sensation of hardness emerges from interaction, not from the presence of a solid substance filling space. Light offers another powerful example of how interactions define reality. Light can behave like a particle or a wave depending on how it interacts with matter. A photon traveling through empty space is not an object with a fixed form. It is an excitation of the electromagnetic field. Its behavior only becomes definite when it interacts with something else, such as a detector or an atom. What we observe depends on the interaction, not on some hidden, object-like essence of the photon. Quantum mechanics pushes this idea even further by challenging the notion that particles have definite properties independent of observation. Certain properties, such as position or momentum, are not fully defined until an interaction occurs. Measurement itself is a form of interaction, and it plays an essential role in shaping outcomes. This does not mean reality is created by human observers, but it does mean that interactions are fundamental to how physical properties manifest. The universe at large scales also reflects this relational structure. Gravity governs the motion of planets, stars, and galaxies not by filling space with solid connections, but by shaping how mass and energy interact through spacetime. In Einstein's theory, gravity is not even a force in the traditional sense. It is a manifestation of the geometry of spacetime itself. Objects follow paths determined by their interactions with this geometry. Once again, behavior is defined by relationships rather than by isolated substance. Even the concept of space and time loses its object, like independence in modern physics. Space is not an empty container in which objects sit, and time is not a universal clock ticking away independently of events. Instead, spacetime is intertwined with matter and energy, shaped by their presence and influencing their motion. What exists and how it evolves are deeply connected through interaction. This perspective has profound implications for how we think about identity and persistence. An object appears stable because the interactions that sustain it are stable. A mountain persists over millennia because the forces binding its atoms and molecules remain in equilibrium. A living organism persists because countless biochemical interactions maintain structure and function. Change occurs when interactions shift, not because an object's essence suddenly disappears. From this viewpoint, reality resembles a process more than a collection. The universe is not a warehouse of things, but an ongoing activity governed by laws that describe how interactions unfold. Particles appear, interact, and transform. Fields fluctuate. Structures form, evolve, and dissolve. What we call objects are relatively stable patterns within this flow. Richard Feynman often encouraged people to think of nature as doing something rather than being something. Physics, in his view, was about discovering how things behave, not about labeling what they are made of. When we focus on interactions, we align with this philosophy. We stop asking what reality is composed of in a static sense and start asking how it works. This shift also helps resolve some of the puzzles that arise when we cling too tightly to object-based thinking. For example, quantum entanglement seems mysterious if we imagine particles as independent objects. Two entangled particles appear to influence one another instantly across distance. But if we think in terms of a shared interaction history and a unified quantum state, the mystery becomes more manageable. The particles are not separate objects exchanging signals. They are parts of a single relational system. The emphasis on interaction over objects does not deny the usefulness of objects in everyday life. Chairs, tables, and people are perfectly valid ways to describe the world at human scales. Physics does not replace these descriptions. It explains why they work. Object-like behavior emerges when interactions are stable, strong, and persistent. At these scales, it is practical and accurate to speak of things as solid and independent. However, understanding that this is an approximation gives us a deeper appreciation of nature. It reminds us that what we experience is a surface-level expression of deeper processes. Beneath the apparent simplicity of objects lies a complex web of interactions operating across many scales. This interaction-based world also encourages humility. It shows that our intuitive categories, shaped by survival and everyday experience, are not ultimate truths. They are effective tools for navigating the world, but they do not capture the full depth of reality. Physics invites us to refine these tools and to accept that the universe may not conform to our preferred ways of thinking. In the end, seeing reality as shaped more by interactions than by objects reveals a universe that is dynamic, interconnected, and profoundly elegant. Stability emerges from balance, form arises from relationship, and existence itself becomes a pattern of ongoing interaction. What we call things are not the fundamental building blocks of reality, but the visible traces of deeper, invisible processes continually at work.